Now look at this.
What's up, about penguins? Today we're going to do topic 2.8 on tonicity and osmoregulation. This topic is basically looking at osmosis. We're looking at which direction is the water going to flow and why. So there's three different types of solutions we can have. So there's a hypertonic solution. If it's a hypertonic solution, it means that it has a higher solute concentration and a lower free water concentration. So it just means that it's high in solute. Hypotonic would be the opposite. It means that there's going to be a low solute concentration and a high amount of free water. Water is always going to flow from a hypotonic solution to a hypertonic solution. This is because a hypotonic solution has a higher concentration of free water than the hypertonic solution that has a lower concentration of free water. Students get really tripped up on this because the numbers that you're looking at aren't going to match. You're going to be looking at the solute concentration. So you're going to see that if you have a 1 molar solution and a 0.5 molar solution, the water is going to move from the 0.5 solution to the 1 molar because there's a higher amount of free water in the 0.5 than there is in the 1 molar. So depending if we're looking at an animal cell or a plant cell is which condition is going to be favorable. The animal cell is going to prefer the isotonic solution because there's going to be an equal amount of water flowing in and out of the cell. The plant cell is going to prefer to be in a hypotonic solution. The reason why is because the water is going to rush into the cell and it's going to fill up that central vacuole. That central vacuole is going to be full of water, which is going to provide that turgor pressure, that pressure against the cell wall that helps to keep it erect. If you were to place an animal cell in that hypotonic solution, you're going to notice that it is going to swell and burst. If you put an animal cell into a hypertonic solution, it's going to crenate or shrivel. And then if you put a plant into a hypertonic solution, it's going to go through plasmolysis, which just means that the plasma membrane is pulling away from the cell wall. That cell wall is stuck there because it's made up of those polysaccharides, specifically cellulose. And so the plasma membrane is going to pull away from that. Bad news, y'all. We got more math. Water potential is calculated by looking at the pressure potential plus the solute potential, and that's going to give you the overall water potential. Water is going to flow from where there's a higher water potential to where there's a lower water potential. The way I remember that is that high water potential means it has a high potential for the water to move. You also might have to calculate the solute potential. So how we've seen this before is that you might have a graph and you have to determine where the zucchini or cucumber or potato is isotonic. So wherever it crosses that x-axis is going to be where it's isotonic. You'll then sub it into this equation for concentration. So I have a practice problem for you. So if we would assume concentrations, 0.5 and that we're at 25 degrees Celsius, so go ahead and plug it in. Let's see if you're right. So if we sub it all into the equation, ionization constant will be 1, concentration 0.5, and then we'll be able to know that our water potential is negative 12.38. 8 just says.